Hello everybody, my name is Daniel Farbowitz, and from the 2020 to 2021 year, I did my MSc at the University of Sheffield, where I did my dissertation under Dr. Jenny Clark, involving transient absorption analysis of nanoparticle ink or water-based solar cells. So the solar cell industry is currently dominated by crystalline silicon solar cells, and that production requires high heat processes, leading to a substantial carbon footprint, in addition to several toxic byproducts. So organic solar cells offer the alternative of low energy, highly scalable cells because the material can be processed via solution. The issue that it comes into is the frequent use of hazardous halogenated solvents in research, which is often not viable in practice. But what if we could replace those solvents with water? So in fact we can. Analogously to soap and oil, if we mix our organic materials with soap and water, we can get bubbled regions of organic material which can be reduced in size by sonication, and the solvent can actually be vacuumed off. And it's been done in practice by Professor Paul Dastor at the University of Newcastle, and they print it using a roll-to-roll process, meaning it's essentially printed like newsprint, and very cheaply, so $10 per square meter. So Dr. Clark and I came at it from a position of, this process gives us easily printed solar cells. Can we help improve the efficiencies by understanding the exciton and charge dynamics? The dominant method used to achieve this is bulk heterojunction type of cell, where you basically take the materials and the solvent, just coat it on your substrate, and then heat it up to get it to organize into larger regions. So with nanoparticles, you have already partially segregated regions, and you would heat it to get it to blend together more. And the donor acceptor pair used by Paul Dastor and myself is P3HT-PCBM, which is not the best in terms of efficiency, but it's very well studied. And one of the clear things is that the literature shows a gap between nanoparticles and bulk heterojunction cells, even though they should be functionally the same once you're done with the annealing. So our method was to produce working solar cells of both types, then compare them both using components and in total with transient absorption spectroscopy. So we're going to hit it with a pump laser to bring our material up into the first excited state, and then a probe laser observe its behavior in that excited state. The major thing I observed is a lack of clear free charge generation in the annealed nanoparticles compared to when you have the nanoparticle inks as a solution prior to being put on a substrate or anything. In fact, when you look at the actual free charge dynamics, the charge lifetimes of nanoparticle solution were actually comparable to that of an annealed bulk heterojunction cell. And so this bears some exploring in itself, but the overall results seem to suggest that there was some over-annealing of the cells that led to phase segregation. And so while there were a number of difficulties in this control, it at least demonstrates the importance of annealing to the final result of the cell. Of course, the main difficulty for me was fighting against lockdowns for lab time. So continuation of this work would involve looking at just the coated version without annealing, performing different annealing times and temperatures, and then also potentially looking at free air exposure prior to film encapsulation. All right, thank you everybody. Bye.